Are we really engineers? More specifically, is software development, or I guess site reliability, a branch of engineering? Now, the affirmative answer is not that interesting. It says software consultant on my business, it says software engineer on my business card. I'm an engineer, that's the end of it. But what I find is that the people who say no, we're not engineers, are far more interesting. And this is because they have wildly different ideas on why we aren't engineers. So why wouldn't software development be a branch of engineering? The first camp is what I'll call the Gerald Weinberg camp. After his quote, "If builders built houses the way programmers built programs, the first woodpecker to come along would destroy civilization." This is the view that we do not have enough rigor to call ourselves engineers, and if we want to grow as a field, we have to finally adopt that rigor. In contrast to him is what I'll call the Jeff Atwood camp. After his quote, "Software development is only like bridge building if you're building a bridge on the planet Jupiter out of newly invented materials using construction equipment that didn't exist 5 years ago." Or, software engineering should not learn from engineering. It is a totally separate field with totally separate constraints, and any attempt to try to make ourselves like engineering is doomed to fail. We have to be our own thing to actually work. Now, in my professional life, I do this thing called formal methods. This is the practice of mathematically proving software and software specifications correct. If you haven't seen it before, instead of doing this, you do this. And like many people in the formal methods camp, I was a firm believer that we are not engineers. If we were engineers, there'd be a lot more money in formal methods. What made me question this view, though, was, ironically enough, someone who agreed with me. Someone who, back in the good days of Twitter, posted this. Contrast this to a building or a bridge, which would not suffer if its creators left. Others could figure out from plans and inspections and take its stewardship. Not so in software. And I thought, I've never built a bridge, but this seems a bit odd to me. I'm not sure that if every single person on a bridge building project was fired, you could just bring in a new crew and they could just start where the old team left off. And then I thought, wait a minute, I just admitted something here. I've never built a bridge. Has Gerald Weinberg ever built a bridge? Has Jeff Atwood ever built a bridge? Maybe these people are only deciding what bridge building looks like based on their own imaginations. Imaginations that probably came from the media. And don't we all know what the media thinks of software engineering? So while my day job is formal methods, my true passion, the one I've never been able to monetize, is falling into rabbit holes. Ask me sometimes what the most important video game ever made is. There is an objectively correct answer to that question. And this question now really stuck in my head. If I couldn't trust all these people I've read about whether or not we're engineering, how could I actually answer this question? It may not be important to a lot of people, but it suddenly felt really important to me. And I decided the only way to get a good answer to this is to talk to engineers. But not just any engineers. They would just make the same mistakes about software as I'd make about traditional engineering. Instead, I need to talk to crossovers, people who have worked in both software and quote-unquote real engineering. People with experience in both. These are the only people I thought could give me a really straight answer on how our fields compared. So I decided to find these crossovers, and I decided to ask them about 3 questions. Number 1, are we really engineers or are we something else? 2, how does the work we do compare to the old work they did in their engineering job? And 3, is there anything that we should learn from the other engineering fields? And is there anything that we could teach them? At the time I had this question, I was fortunate enough to be a pretty active Twitter power user, and that made finding people easy. I just asked Twitter. Man, everyone remember Twitter was good? Just kidding, Twitter was never good. In the end, I compiled 12 hours of interviews of 17 crossovers representing 6 different disciplines. I tried to get multiple people in each discipline in order to make sure I didn't get any biased view, not just one mechanical engineer, but several. Everything I'm talking about going forward is based on these interviews. It's my synthesis, but their knowledge. So let's start with question 1. Are we really engineers? Turns out that's not the right question to start with. The real right question to start with is, what's engineering? Now, when we think engineers, we normally think of the people who go build bridges, or buildings, or roads, or Ferris wheels. As one interviewee put it, anything required for a living city. But these people are called civil engineers, and they only make up about 20% of engineers in a given country. I checked this for the United States, for Ireland, for Australia, for a few other places. This ratio of 1 to 5 is pretty consistent. The rest belong to a bunch of other fields, things like mechanical, electrical, chemical, nuclear, and mining engineering. And with so much diversity, so many different kinds of engineering, it becomes very hard to come up with a few things that accurately describe all of them and only them. Let me give you 3 common things people say describes engineering: that it's physical, that it's consequential, that it's licensed. There are other ways that people try to describe it, but I think these are good ones to start with. So, the idea that engineering is physical. This is most often used to delineate software as not engineering. They work with metal and concrete, we work with bits and bytes. Therefore, why would we be engineering? Well, one of the first people I talked to was a core C Python compiler developer. But before that, he was a systems integration engineer at Boeing. I asked him what that actually meant, systems integration engineering, and he gave me an example of one of his last jobs. They had an airport. Airport had to do radio communication with a plane. The airport hardware and software was being developed by a separate team than the plane hardware and software. These teams didn't know each other existed. They certainly never talked to each other. Each of them could easily make decisions that would make it impossible to work with the other team. For example, an airport might broadcast and receive on a radio band that an airplane might be legally forbidden from using. His job was to get in between those two and intermediate, and make sure that they could agree on common interfaces and protocols. And when, inevitably, they had already made a decision that was incompatible with the other side, he had to find some way to work around that, some bridge between the two. Oh, and also, this entire time, this is being mediated through an antenna array that was already being built with its own protocols interfaces that he couldn't talk to at all. But he still had to work with their constraints. This is engineering. It is certainly not physical engineering. Incidentally, he told me that systems integration engineering was a subset of what he called industrial engineering. He recommended I buy this book, The Handbook of Industrial Engineering. I did. I did not bring it because I am not bringing a 3-kilogram book across the Atlantic. But I want to point out a couple of interesting principles in this book, how they start and say the fundamental principles of industrial engineering that all industrial engineers must always keep in mind. The first is the uniqueness principle. Each project should be regarded as different from previous seemingly similar projects. The people design principle. Stakeholders, like you or me, must have a role in finding and implementing the solution. Does this remind you all of anything? So we can see that engineering doesn't necessarily need to be physical. The next common thing given is that engineering is consequential. The idea being that if software fails, you just reset or you find another computer. But if a bridge fails, people die. Until we're actually doing stuff that that has consequences, how can we be engineers? Now, normally, here's what I'd be explaining, that actually a lot of software does have really serious consequences. But you're all SREs. You know what happens when the site goes out. You know how much money that costs a company. So instead, I'll just cover the other side of things. Is all real engineering always high consequence? Show of hands, who here flew on Aer Lingus? Great. Did any of you get these? So, I don't know, on my flight, I got these earbuds. Everybody on the flight got the earbuds. I checked later, they cost about 10 cents to manufacture. Less than that, that's how much they sell for. Less than that to manufacture. They also say that they're only single use. So after somebody uses them once, you just throw them away. And I mean, let's be honest. If somebody accidentally breaks their set of earbuds, just give them another pair. Raise your hand if you think the work you do is more consequential, as in more people's lives will be hurt than these earbuds. Okay, I'm seeing some hands are actually down. Come on, people, have some dignity. So, engineering doesn't necessarily need to be consequential. Now, the last thing I often hear is that engineering is licensed. And this is often used as a simple slam dunk argument. Like, oh yeah, in software we don't have licenses, so how can we call ourselves engineers if we don't have to go through a licensing process? And here's where things get a bit tricky. Because it's true that in some places, did the map go up? Okay, yeah, it's a bit faded. In some places, like Canada and Germany, you can't call yourself an engineer without accreditation. But there's a lot of other places, places like the United States, most of the European Union, Ireland, which is part of the European Union, and China, where you can actually do engineering without a license. What you cannot be is a chartered engineer, someone who can sign off on designs. But the chartered engineers only make up a tiny minority of engineers, and most of the engineers working under them do not have licenses. There's even places like the United Kingdom where this distinction doesn't exist at all. Anybody can sign off on drawings. Licensure is a political and legal concept. It is not an essential description of the nature of our field. So I do not think that engineering is licensed really defines engineering. I could go through some more definitions of engineering, but they're all going to have the same problem. Either they include something that we all agree is not engineering, or they exclude something that we all agree is engineering. Fundamentally, I was only able to find one single definition of engineering that accurately described what engineering is. Engineering is what engineers do. This might sound silly, but this is how it works. If enough engineers agree something is engineering, it's engineering. If enough say it isn't engineering, it's not engineering. Fact of the matter is, that's as simple as it goes. So, this made my question very easy. Instead of having to pierce together all these different definitions of engineering and figure out where software fit, I could just directly ask these crossovers. Do you consider your current work a form of engineering? Of the 17 people I talked to, 2 said no, and 15 said yes. So everybody, we're engineers. Congratulations. I'll be honest. I was not expecting this result. I was expecting the opposite. I was expecting all of these crossovers to tell me that no, the work we do is not engineering, and we shouldn't dare to call ourselves engineers, and we better really shape up if we want to take that term. But I was wrong, and that's why this kind of research is so valuable. You don't know what you're going to find, but what you're going to find is something you can be confident in. Going forward, I'm going to stop calling it software and real engineering. Instead, I'll use software and traditional, or trad. Now, I said that they said we're engineering, but there's actually a bit of nuance to that. In most fields, there's a distinction between engineering and tradecraft. Electrical engineers are doing engineering. Electricians are doing tradecraft. They're both really important, highly skilled work, but they focus on different things in different spaces. So if software is engineering, what do we call tradecraft? I don't like the term programmer here because there's a lot of people who do programming. Artists, academics, secretaries, kids. And I hate the term software developer for this, because if we're being honest, a lot of software developers are just doing full-on engineering. But I feel there is some value in trying to figure out what this term is. Partially because these fields are surprisingly much closer than in other fields. People often move between software engineering and this other form of work. Sometimes it's people who change jobs and decide they don't want to be doing the same level of engineering. Sometimes it's people who promote themselves upwards. There's actually a really specific reason for why these fields are so close compared to other fields. I'm going to talk about that later. But for now, I want to focus on one way that that other people have tried to define this distinction. Software crafters, or historically craftsmanship. That comes from this book, Software Craftsmanship, The New Imperative, by Pete McBreen. Unlike the engineering book, I was able to bring it. In this, he defines the difference between software engineering, which is large-scale projects of hundreds of people working with rigorous principles, doing routine work, and software craftsmanship. People who are working in highly unknown environments where theory diverges from practice, who have to use their own creativity, intuition, and expertise to get work done. I started to see more and more of this belief as I read more and more of the book. This very clear distinction he has between engineers who do routine, rigorous work, and craftsmen who do very unique, creative work. I'm pretty sure that he talked to 0 engineers in writing this. And that brings me to part 2. How is software different from traditional engineering? In other words, are we special? We have this view that software is a totally unique field, and normal engineering principles and practices do not apply. After all, it's not like anybody's ever had to move an entire bridge after it's built, right? But we redesign software after it's released all the time. If I had to summarize the common conceptions of the differences between our fields, I'd put it like this. Software, agile. Waterfall, traditional. Software, unpredictable and informal. Traditional, predictable and rigorous. Are these true? In most cases, a little. Starting with software as agile. This is the foundational myth, the national epic of our field. In the bad old times, we had waterfall. We would move linearly from planning through designing, building, testing, and deployment. We got this idea from the other fields of engineering where it worked supremely well, but it turned out to be a terrible fit for software. So in the 90s, people invented agile. We threw waterfall in the trash and have been living happily ever after. Now, I'm not going to discuss the merits of waterfall and agile here, but I do want to ask one simple question. Do other fields of engineering actually practice waterfall? Well, construction engineers do. A lot of buildings are built in a very highly waterfall way. Software is very agile. Everything else, actually in the middle. You see, people hate waterfall. But there is one principal thing that divides waterfall work from agile work, and that is the cost and speed of iteration. The harder it is to iterate, the more you do waterfall. The faster you can iterate, the more you do agile. And this actually happens in every field. As the field finds weight, so fields are constantly looking for ways to iterate faster so they can be more agile. And the reason why is because faster iterations in agile are much better at dealing with unpredictability. Because this idea that engineering is predictable, 2 people laughed at me when I brought this up. For example, you know that whole thing about like people don't have to move bridges after they're built? I talked to a couple people who had to move bridges after they're built. There are entire books online about how to move bridges after they're built. It is an entire industry of moving bridges after they're built. I heard a lot of crazy stories from everybody. But just to sort of give you an idea of the breadth, I'm going to cover just 3. Story number 1, electrical engineer, working on a circuit. Had it mostly figured out, except needed a single CPU to go into the circuit. He was working off a catalog of 1,000 different CPUs and found that some actually fit his criteria exactly, did exactly what he wanted with exactly the limits he needed. Unfortunately, none of these could be bought in bulk because he needed 5,000 of this delivered at a time, and most of them can only be delivered by the dozens. In fact, of these 1,000, only 250 could be delivered. I know it says 293, but lag. And it turns out that most of these 250 couldn't be delivered on time because they had a very tight schedule to work with. Going through that and talking to every supplier, he reduced this number of viable candidates from 250 to 8. 8. And none of them fit his work at all. But, well, he had to do something, so he picked the one he had the most experience with, redesigned his entire circuit, and just got to work. Quick question. Has anybody ever had to redesign their entire app because of a really weird framework or API? Yeah. I have. You have. Yep. Happens in electrical engineering too. Okay, story number 2. This is a guy who was a naval engineer. He worked on offshore oil rigs. His job, for the most part, was to test them to make sure they didn't vibrate too much. Because if an oil rig vibrates too much, you're going to be thrown out of your bed when you're sleeping. That's really bad for everybody. There's regulations on that. Most part, pretty straightforward job. But one story he had was having to put in a new piece of equipment. Problem is, didn't fit on the first story of the oil rig. How do you fix this? Well, one way to do it is to saw a hole in the floor/ceiling, shove the entire thing in there, put a new floor on top, just 1 meter square around the 4-inch lift of the machine, and then put up a big sign saying, "Warning, do not trip over this." Like software, traditional engineering has a lot of kludges and technical debt. Unlike software, that kludge lasts forever, and everyone can see it. Okay, last story, my favorite. Mining engineer. Help with the design of new mines. Now a Scala programmer. He was working on a mine, I believe, in the Canadian wilderness, which had its own interesting consequences of legality versus First Nation and Canadian government stuff. But the story he told me was working on a very boggy terrain. Most of the ground was marshy and had to be dug up to build the mine. But you can't just delete the dirt off your hard drive. You have to put it somewhere. Shipped it all off to an offshore supply depot. And this worked for weeks, until one week, all the trucks came back at once. His parent company lost the contract with the supply depot, and they said, "Get rid of all this dirt right now." So now where do you put it? Well, only thing we could do, take their really nicely laid out, perfectly efficient camp, rip the whole thing up, dump the dirt all in the center, and rebuild the camp around that. This person also told me about some of the ways that people try to iterate faster. In fact, mining engineers were experimenting with Agile as early as the 1950s with a new Austrian tunneling method. But people are always looking for new ways and new technologies that help them figure out their ideas just a bit faster, let them be a bit more agile. One way you could have actually seen downstairs, 3D printing, like in the Grafana booth, extremely popular now in mechanical engineering. The most popular new tool, the most exciting thing people have developed, though, software. This is a finite element diagram. It shows what happens if you crash a simulation of a car into a simulation of a wall. Not as good as doing the real thing, but doing the real thing costs thousands of dollars per car, right? You don't want to do that until you figured it out here. People use software to iterate faster, to be more agile, to need less rigor. And that brings me to part 3. Engineering is more rigorous. This is true, sort of, but for a very specific reason. The first reason is that some regulations require some degree of rigor. Far more common in far more fields is the cost of iteration. More expensive iterations mean you want to do more upfront planning because that saves cost. But in cases where you can get away with that upfront planning, often you do, because experiments and just trying things out is its own form of rigor. One field that can iterate pretty quickly is chemical engineering. And one chemical engineer told me about how they solved an incident that happened at their plant. Their plant made a special kind of rubber. For the most part, it worked day in, day out. One day it just stopped working, just nothing would form. Could not make rubber anymore. Now, observability in other fields is much, much worse than in software. It's not like you can just drop a breakpoint debugger into a pipe flow. Normally, trying to debug these issues requires very carefully going over every part to try to find the quote-unquote root cause of the issue. Or, as one of his coworkers pointed out, you can just stop the entire factory and then start it again and see if that fixes things. It did. They said, "That was weird," and just continued on with their day. Often, though, the easiest way to deal with these issues is to get the programmers to deal with it. One hardware engineer told me about one electrical engineer made hardware for a company and said that at the company, they had a big list of every single project they had and whether or not it required some sort of software fix for an electrical engineering issue. All of them did. The fact is that because we can iterate so much faster than other fields, they often rely on us to fix their mistakes. And sometimes this can have disastrous consequences. In 2019, two 737 MAX Boeing aircraft crashed. They were flying normally and then suddenly went into dives. The pilots couldn't pull them out of the dives, and because of this, over 300 people died. Initial reports blamed software, the MCAS flight stabilization software, which had a bug. Later investigation found that that wasn't actually the quote-unquote root cause. You see, when they were designing the 737 MAX, they had much larger nacelles. These turbines over here were much larger than an early aircraft. And late-stage aerodynamic analysis showed that this made the entire airplane unstable. Normally what you'd do here is you'd go back and redesign the aircraft to actually be stable with these larger turbines. But this was going to cost a lot of money, and they decided they could iterate faster by having the software people write stabilization software that fixed it for them. And then when that software had a bug, people died. So we see that a lot of the ways that we think software and traditional engineering are different don't quite hold up. They're similar in all these ways that we do not expect. So is there anything that's different? There are actually a few things. One is velocity. This is unquestioned. Fast fields, in other disciplines can iterate in like hours. We can iterate in seconds. We can deploy an entirely new set of software in a few seconds. The second thing that's maybe a bit more obscure is mathematical basis. I've often heard the myth that mathematics is not needed for software. People say they learned all this math in high school and not once was it ever needed. This is because historically, high school and early college math is heavily geared towards the needs of traditional engineering, often highly continuous mathematics, things like differential equations, or calculus, or trigonometry, or algebra. But software is much more heavily dependent on discrete mathematics. These are things like combinatorics, or formal languages, or logic, or graph theory. We just don't realize that we're doing a lot of math. For the same reason we don't realize that 16 plus 7 is math. We just do it so often it feels implicit. This actually inspired me to try to make it explicit. For the past few months, I've been working on this book, Logic for Programmers. It's designed to show programmers that, yes, they are in fact using mathematics in their day-to-day work. It doesn't have to be scary. It's something they can do and something they can find useful. And then what I'm trying to do is show them how knowing this explicitly as opposed to implicitly opens up a lot of really cool techniques. Things like advanced forms of testing, case analysis, better database constraints, and access to really unusual and powerful tools like planner programming and constraint solvers. I'm still working on it. I've released about 4 versions of it right now. I'm hoping to have it finished in 2025. But it's already got like 25,000 words, 9 chapters, and 40 exercises. You can also find me after the break. I can just give you the discount right there. It's not a big deal. The last thing that is different is consistency. Software is so much more consistent than other fields of engineering. Like, take a sort program. This is quick sort. There's maybe some edge cases, like if you have extremely large lists or extremely high numbers. But for the most part, on most versions of Python, in most computers, on most CPUs running most operating systems, with most inputs, this will sort the same way every single time. In contrast, traditional world, the physical world, is extremely inconsistent. Like, say you buy a box of 1,000 capacitors. Capacitors are measured in farads. If you buy 1,000 100 microfarad capacitors, most of those won't actually be 100 microfarads. That's because, at least with this spec sheet, it has a 20% tolerance. Some will be 80, some will be 120 in the same box. Only way to know which is to test them one by one. Also, see that little at 120 hertz set 20C? Go above 20 centigrade, all bets are off. You can do whatever you want, do not have no idea. This really profoundly shapes what traditional engineering actually looks like. One quick anecdote by one person. Whenever they were working on any mechanical infrastructure and they needed a new part, they would ship off their specs to 3 separate suppliers. And each one would consistently give back a slightly different part. Different variations, different properties. None of them did quite what they want, but they had to work with one of them. They could not get exactly what they wanted every single time. They'd pick the one that was closest, then rejigger all the other parts of the design to work with this new slightly off part, and continue and do this for the next part, and then the next part, and then the next part. This inconsistency-consistency thing is a huge deal and a huge difference between our fields. So there do, in fact, exist pretty significant differences between software and traditional. The speed we work, the mathematics we use, the consistency of our field. So I'd like to ask you, does this make us special? In my opinion, no, it does not. We're not special. The reason why is because, yes, there are some things that make software different from civil and mechanical and electrical and chemical engineering. But there are also things that make civil engineering wildly different from mechanical and electrical and industrial and software, and things that make chemical engineering different, and things that make industrial engineering different, and things that make bioengineering different. The point of us being an engineering field is that we have a lot more in common with those other spaces than we have different. And I think that's a good thing, because it means that there's a lot we can teach and learn from each other. Now, here's a confession. I said this was an interviewing project. I kind of screwed this part up. I did not do a great job in getting what we can learn from those fields from those people. I did not do a great job asking the questions or synthesizing the information. I did find a few things, but I think this is the part I'm least confident about. A couple things you might not be surprised by. While they like the iteration speed we could work at, they wish they had more upfront planning time. And a few engineers lamented that in their old job, they felt they had a much greater sense of responsibility to the customer. In their new work, they felt more disconnected. Something I think a bit more surprising is this, the SnapFit handbook. This was recommended by one mechanical engineer I talked to. Do all you know what a SnapFit is? One sec. And here's where I pretend to be typing and changing my my slides, but my computer's gone. Anyway, that's a SnapFit. It's basically the tiny part that goes in that goes inside a remote that basically fastens it in place. And this was an entire book on these, an entire book on what kinds of plastic you want to use, what kinds of dimensions you want, the cost of manufacture, stress levels. Very, very focused on this very small topic. And I think that's interesting, this idea of creating resources about our components. There's a lot of books we have about our tools, like the Docker Cookbook or Logic for Programmers, but not a whole lot about the things we build with these tools. I'm talking about things like tag systems or API versioning or user profiles. Issues that every single engineer has, no, not every single engineer, but like a lot of engineers have, and a few people actually have hard-earned knowledge on. I think creating more of these resources could actually do a lot to improve the state of our field. Now, I said that I kind of screwed up finding out what we can learn from those fields. I did a pretty good job on the other part, what they can learn from us. And the reason why is because everybody said the same two things. Everybody had scattered ideas on like, oh, what could they bring towards software? But everybody was very, very clear on what we could bring back. First thing that everybody mentioned, SREcon, Europe, Middle East, Africa. Most fields of human knowledge only have two kinds of conferences. They've got academic conferences for sharing research, and trade conferences where companies try to pitch each other on products to buy. Software engineering might be the only field where we have a third kind of conference, the practitioner conference, the conference where a bunch of experts get together just to talk to other experts and share their knowledge. So many people were jealous of this. So many people wish they had that in their old job. We also are one of the most open industries out there. We are willing to put so much of the information we create free and make it available online, and make our tools open source, and make how to use those tools freely available too. Earlier I said that there's a very small gap between software engineering and this other kind of craft. That's exactly why. It is so much easier to learn to be a software engineer than to be an electrical engineer or any other kind. Because I know this might sound kind of hard to believe, but not every single home has a mass spectrometer. But everyone has a laptop. Anyway, that's the minor thing. This is the thing that like a lot of people mentioned, but like wasn't unanimous. Because there was actually one thing that every single person, all 17 people I talked to, brought up explicitly. The one thing that they most desperately wish they had at their old job. Git. Now, version control does sort of exist in other fields. It's most often called change management software. But that's kind of like saying that you don't need laptops because you have a 4-function calculator. What we have with Git and Mercurial and all those other version control things is something so far more advanced and so far more powerful than what these other fields have seen that they are very, very jealous and wish they had it. Even being able to do basic things like git pickaxe or git bisect are unheard of. And I think that if we could make a tool that wasn't as hard to use as Git, because Git, let's be honest, is really hard to use, but was a little bit easier and a bit more focused on the everyday user experience as opposed to just raw power, this would do an incredible amount to amplify the productivity of other fields. So, in conclusion, we are engineers, we're not special, and there's a lot we can teach and learn. If you're interested in this research, I have a couple of resources. The first one is the talk page. I'm going to put all the questions I get up on there, and there's also links to the slides and references I used. I also have a 3-part, 10,000-word write-up on this project that goes into much more detail with a lot more examples. Unfortunately, I cannot share transcripts. Those are private. Last thought I'm going to leave you all with. This was really easy. I had a question. I found people. They were willing to talk to me, happy to share their knowledge. I learned a lot. If this in any way interests you, I just recommend trying it yourself. There's a lot I did not ask about. Things like the actual techniques, like lockout, tagout, or what meetings look like, or what engineering looks like in the global south. If you're ever curious about any of these questions, just try doing this yourself. Find people who know this information, just talk to them. And I think that there's a lot we can learn not just from other engineers, but from every field of human knowledge. Everything from journalism to social work to warfare. So I'd recommend, if this at all interests you, just find people, talk to them, learn, and share what you learn. Thank you very much.